All right, hello everybody. This is Mr. Combs, and I realize that we don't have that you all are not in classes today. Um, but I thought that I would log on just in case someone logged in to the Blackboard session, and I will record this session. I am recording it so that you can watch it later because we're going to talk today about logistic growth. This is the last topic dealing with growth. So next week we will start talking about finance, and we'll start out talking about um, um, simple and compound interest, and then we'll talk about loans and annuities and things like that. But this is the last time, or this is the last topic with growth. We've talked about linear growth, we've talked about exponential growth, and now let's talk about logistic growth. So this information sheet or information guide is listed in MyOpenMath. I've stopped actually listing things in Blackboard. The only reason why we're still using Blackboard, or I'm still using Blackboard, is because that's where Blackboard Collaborate is. Everything else that you need will be in MyOpenMath. So really, MyOpenMath is the only thing you need to access, except on Mondays and Wednesdays when I'm not at one of the schools, because then we'll use Blackboard Collaborate. Okay. All right. So let's go ahead and talk about growth, logistic growth. So populations of living things tend to grow exponentially, and we've been talking about growth in terms of a lot of things. We talk about growth in terms of living things. We talk about growth in terms of money in a jar or bank accounts, that kind of thing. But when you're dealing with things that are living, those populations tend to grow exponentially. So as we have seen, populations growing exponentially can get quite large very quickly. Think of Connor's shoebox money. After just 18 years, the amount that began as $1 grew to almost $1,500. And that's, I mean, when you start out as small as $1 and you grow to $1,500, that's pretty quickly. Or just in 18 years, that's pretty quickly, and that is quite large as well. However, when dealing with living things, this growth is rarely without constraint. For example, a fish population growing exponentially in a pond can be restricted by being heavily fished, or there may only be enough food and habitat to sustain a certain number of fish. So things that are growing exponentially without any sort of constraint or without any restrictions can get very large very quickly. However, there are rarely, when dealing with populations of animals or people or plants, there are rarely no restrictions. So things are usually, or growth is usually constrained, and that's where logistic growth comes in. So logistic growth will be a way to measure populations that would grow exponentially but have some sort of constraint. So one of the terms that we need to talk about is carrying capacity. We refer to the maximum amount size of a population that a certain environment can sustain as the carrying capacity. And in fact, I think that I meant to delete this word amount. So just if you want to cross that off. I will fix that on the information sheet. So we refer to the maximum size of a population that a certain environment can sustain as the carrying capacity, represented by the letter K. So the carrying capacity is the maximum number of individuals that a certain environment can hold. We use logarithms to model growth of populations that have a definite carrying capacity. Well, we really don't use logarithms. We use logistic growth. And I'll change this, sorry. So we use logistic growth to model the growth of populations that have a definite carrying capacity. Developing a logistic model is often a complex process, so we will just use a model already developed by mathematicians and scientists. The type of model that we're going to use is generational growth, a generational growth model. So we're going to see, or this will tell us, that if there is a carrying capacity for a certain population, this will tell us how big the population or how much the population increases each year over time. So populations that exhibit generational growth usually have a single or small number of specific breeding seasons rather than offspring being born steadily throughout the year. The model for generational growth is given in a recursive formula below, and there's unfortunately no explicit formula for this type of generational growth. So if we want to look at this type of growth, what we have to do is we have to start with year 0 and find year 1 and find year 2 and find year 3 and so on. We can't just find year 15 without finding the others because we have no explicit formula for this type of generational growth. All right, so generational logistic growth. If a population that would normally grow exponentially, so normally it's going to grow exponentially with a growth rate of R, has a carrying capacity K, so there is a carrying capacity here because it is growing in a constrained environment, then the population behavior can be modeled using the following. So if I want to know the population for a certain year, so, year 0 is the year we're starting with. Year 1 would be the next year, year 2, and so on. Then I use this formula. So I take the year before, and I add the rate times 1 minus the year before, the amount for the year before over K, and I multiply that by the amount for the year before. All right, so let's consider this situation here. It says a meadow is currently home to a population of 200 rabbits. Research shows similar meadows have a carrying capacity of 2,000 rabbits. So I know that I'm starting out with 200 rabbits, and I have a carrying capacity of 2,000 rabbits. Absent any restrictions, the rabbits would grow by 50% per year. Predict the future population using the generational logistic growth model. All right, so we know that if we could use the exponential model if they were not restricted by the environment, but they are. The environment can only hold at most 2,000 rabbits. So we know we're going to use the generational logistic model to do this. So P sub 0, we know the meadow is currently home to 200 rabbits. So we know that P sub 0 is 200. Now we can use that recursive formula to find how many rabbits there are next year. So what we're going to do is just fill out this formula here specifically for this situation. So P sub 1, that is the next year. So if there are currently 200 rabbits, how many rabbits will there be next year? All right, so P sub 1 will be P sub n minus 1, so that's P sub 0. That's 200. Plus the rate R, that's 50% or 0.50, or you can just say 0.5. times 1 minus 200 over 2,000. 200 is the p sub 0 and 2,000 is the carrying capacity. And I'm going to multiply that by 200. So when you do all that on the calculator, what you're going to end up getting 290. So P sub 1 is 290 rabbits. So the population increased by 90 rabbits. All right. So we can come up with a general formula for this situation for any P sub n. And this general formula we'll be able to use to help us find the rabbit population. I want to find the rabbit population for 20 years. Now don't worry, we're not going to have to do these calculations. I'm going to show you a way to do this on the graphing calculator. Alright, so P sub n, we can say that P sub n is equal to P sub n minus 1 plus, in our situation, the rate is 0.50 times 1 minus P sub n minus 1 all over 2,000 times P sub n minus 1. So that will be a formula we can use for our specific situation. All right. Now, you could use this formula as we fill in the chart each time, but I've got a quicker way that I want to tell you. So we know year 0. We know year 0 is 200. We know year 1, that's 290. All right, but what about year 2, year 3, year 4? Okay, if you have your graphing calculator, there's a really quick way to do this. And I'm going to stop sharing the document now. We'll have to write this back in. So make sure you have that. I'm going to stop sharing the document, and I'm going to start sharing my screen. And we will... look at the calculator on my screen here. Okay, so there's my calculator. If I show, I mean, it has this sort of infinity thing going on here, so I'm going to bring up maybe the desktop. Okay, here we go. So if you can see my screen, you see this TI-83 Plus calculator on my screen. I'm going to turn this on, and when you turn it on, what you need to do is hit Y equals. Now, what I'm going to do is I'm going to use X and Y in place of P sub n and P sub n minus 1. So let me bring up here Paint just so I can write this. So in the calculator, I'm going to use, instead of P sub n, that's going to become Y in the calculator. So Y1 right here. And then P sub n minus 1, that's going to become X. So I'm going to put this formula into the first plot, or the first Y equals, in the graphing calculator. All right, so here's what I'm going to do. So my formula, if you remember, is P sub n is equal to P sub n minus 1 plus 0.5 or 0.50 times 1 minus P sub n minus 1 all over 2,000, and then I'm going to multiply that by P sub n minus 1. So remember, in my formula in the calculator, I'm going to have y as P sub n and x as P sub n minus 1. So here's how I'm going to enter it in. I'm going to say x, and that's this button right here. So x plus 0.50, that's 0.51. 0.50 times 1 minus, and because this is going to be a fraction over here by itself, I'm going to put parentheses around that. So I'm going to say 1 minus parentheses x divided by 2,000, close the parentheses. Now I need to close this parentheses and multiply that by x again. And when I do that, then I'm going to hit second and graph, and that's going to bring up a table. Now what you want to be able to do is you want to be able to enter y values into this table. So I'm going to go to second and window, and that will be table set. And you want to change the independent variable from auto to ask. And then hit second table again. And that's going to allow me to ask or to put in the x values that I want. Okay, so the first x value I want is 200, because 200 is the original population, and when I put 200 in for x, y will tell me what it is during what the population is during the first year. So 290, which is exactly what we thought. The next thing we're going to do is we're going to put 290 in, and that's going to tell us what the population is for year 2. And I'm going to, you'll see later when we go back to the document, I'm going to round up. So I'm going to make this 414 instead of 413.98. Now, I'm going to take 414 and put it in, and that's going to tell me year 3. So this is year 0, this is year 1, this is year 2, this is year 3, 578. So I put 578 in, and that's going to tell me year 4. So year 1, year 2, year 3, year 4, and so on. So if I go back, I'm going to stop sharing the screen. I'm going to start sharing my file again. So if I go back here and I fill in the chart here, I'm going to fill it in with 200, which is what we knew the population was. 290, we found that one by hand. And then the rest of these we found on a calculator. So year 2 is 414. Year 3 is 578 we found. And if you continue doing this, year 4 is 783. You'll find that year 5 is 1021, so 1021. 1271 is year 6. Year 7 is 1503. You can follow along on your calculator to check these. Year 8 is 1609. So what do you notice? I notice that I'm growing pretty quickly, right? I mean, I'm already in year 8, and I started out with 200 fish. Now I have 1,600 fish, right? So, in only 8 years. So I'm growing pretty quickly. So let's see. Year 9 is 1821. Year 10 is 1903. So something here starts to happen. What am I at 1903? What am I getting close to? I'm getting close to the carrying capacity of 2,000. So something starts to happen. In year 11, according to this model, I don't grow as much because I'm getting close to the carrying capacity. So I have 1903 in year 10. In year 11, when I use the model, I just have 1949. In year 12, I have 1974. So as I'm getting close to the carrying capacity, I'm not growing as quickly. I'm not adding as many fish each year. Let's see, 13 is 1987. And you know, there might be many reasons for this. The more fish may die because there's not enough food to sustain the fish. Let's look at 14. 14 is going to be 1994. 1994. 15 is going to be 1997. 16, 1999. 17 is going to be 2000, and you're going to notice that whenever you have 2000, it's going to be 2000 from there on out. So what could really happen realistically here is the population after year 20 could still be around 2000. But sometimes you see populations that go into decline after the carrying capacity is reached. So you'll notice here that we start growing out rapidly, and then as we get close to the carrying capacity, the growth starts to slow down. That is a characteristic of logistic growth. All right, let's look at another situation. It says a field currently contains 20 mint plants. Absent constraints, the number of plants would increase by 70% each year. But the field can only support a maximum population of 300 plants. Use the logistic model, to predict the plant population for the next 3 years. So we need to find P sub 1, P sub 2, and P sub 3. We know that P sub 0 is what? 20. There are 20 plants. So what we need to do is we need to find a general recursive formula for the growth in this case. Then we can use that to find P sub 1, P sub 2, and P sub 3. So let's, over here on the side here, down here in the bottom corner, let's come up with a formula for P sub n. Well, I know that P sub n is always going to be P sub n minus 1 plus the rate. So they're growing by 70%. Then I'm going to multiply that by 1 minus P sub n minus 1 over the carrying capacity. And that's 300. And then I'm going to multiply that again by P sub n minus 1. So we're going to use this to find P sub 1, P sub 2, and P sub 3. So there are 20 plants now. How many plants will there be next year? Well, let's see. So P sub 1, P sub n minus 1, I'm just going to, if I'm dealing with P sub 1, I'm going to substitute the number from P sub 0. If I'm dealing with P sub 2, I'm going to substitute P sub 1. So here I'm going to put 20 plus 0.70, you can write 0.7 if you want, times 1 minus 20 over 300 times 20. So 20 plus 0.7 times 1 minus 20 over 300 times 20. And when I do that, what I'm going to get is approximately 33. I get like 33.0667, but I'm going to get approximately 33. So I'm going to leave this as 33. All right, P sub 2, the first thing I'm going to do is I'm going to use, instead of 20, I'm going to use 33. Let's do this in a different color just to help it be contrasted. So 33 plus 0.70 times 1 minus 33 over 300 times 33. And that's going to give me approximately 54. It's going to be 53.559, so I'm going to say that's approximately 54. And let's do P sub 3. So for P sub 3, I'm going to put in 54 plus 0.70 times 1 minus 54 over 300 times 54. And when I do that on the calculator, I'm going to end up with 84.9, or approximately 85. So it says, use the logistic model to predict the plant population for the next 3 years. 33 in year 1, 54 in year 2, and 85 in year 3. So this is still, we haven't reached our carrying capacity, or we haven't gotten close to our carrying capacity yet. So this is still pretty rapid growth. We're increasing quite a bit each year. To start out with 20 plants, right? Okay. So we've actually talked about 3 different kinds of growth. We've talked about, let's see, I'm going to use, I guess, red here. We've talked about linear growth. And for linear growth, if I were to draw a graph or a picture of what that kind of growth would look like, it would just be basically a straight line. Because linear growth is constant. So the amount of growth each year is going to be constant. It's not going to change. So think of Connor's money in the jar. He puts $25 each month. So I'm going to increase my amount by 25 each month. That's not going to change. So that's going to be constant growth. Then we talked about exponential growth. And for exponential growth, what happened was things started growing okay, started growing, at a nice pace. But then as we got further and further along in time periods, the growing started to increase rapidly, right? Once you've got so much money in the shoebox, then if you take half of that and add it to it each year, since that amount in the shoebox is growing, the half amounts is growing as well. So what happens with exponential growth is you grow, and then you have a really rapid increase in growing. So it shoots up. So this is exponential growth. We start out slow or start out regular, I guess. We might say start out slow. And then as the growth or the time periods increase, the growth becomes more the growth happens more rapidly, I guess is what we want to say. And now we're talking about logistic growth. And for logistic growth, there's always going to be some carrying capacity, something or some amount of the population that the environment can sustain. So what's going to happen is, as you grow with logistic growth, you're going to grow maybe quickly at first, but then as you get close to the carrying capacity, the growth is going to taper off, and you may not grow as quickly. So those are the three types of growth that we've studied, and you may have some questions in your homework and on a test that ask you to look at a situation and tell me whether it's linear growth, exponential growth, or logistic growth. And I'll use L, X, and log for each of these growths. So here it says we have studied three types of growth, linear, exponential, and logistic. Consider each of the following situations. Label each as an example of linear, exponential, or logistic growth. Excuse me. All right. So the first situation says it may be relatively easy to shed 5 pounds within a week or two, but then the progress slows. Each successive pound of fat loss is more stubborn than the last. What do you think this type of growth is? Yeah, I think this is logistic growth. And the reason why it's logistic growth is because you're losing pounds quickly at first. Maybe it's relatively easy to shed 5 pounds within a week or two, but then as you get to the third week or the fourth week or the fifth week, maintaining that constant rate of weight loss is a little harder. So this would be an example of logistic growth, because what you're doing is the number of, if we think about number of pounds you lost as what's growing, you grow quickly, you lose a lot of pounds at first, and then as you reach the threshold, we call it, you don't lose as much. And so with losing weight, there is an amount under normal conditions that your body is fine at that weight. So there's an amount that you want to sort of stop at that's the carrying capacity. You don't want to just lose weight exponentially, because then, in 4 years you'll be down to an unhealthy weight, right? So that's logistic growth. It starts out quick. It becomes slower as you go. There's a definite carrying capacity. There's a definite total amount of pounds that you want to lose, maybe if you're trying to lose weight. Number 2 says, thanks to the power of compound interest, your retirement savings start out as small as a small treasure in the early years, but balloon in size during the final decades or two of savings. That's definitely exponential growth, right? Because we start out slow, but as we get more money in the account, the growth starts to go quickly. So that's definitely exponential growth. And then Maria opened up her ice cream parlor with 20 flavors, and each month she adds one flavor to the menu. Now Maria has 38 flavors on the menu. This is an example of linear growth. Because we are constantly adding one flavor each month, right? So after the first month, we will have 21 flavors. After the second month, we will have 22 flavors. After the third month, 23 flavors, and so on. So that's definitely linear. So you may have some questions like this in the homework. I think the homework questions focus on graphs more, but you may have some questions on a test that give you situations like this and ask you to determine whether the situation describes linear growth, exponential growth, or logistic growth. All right. Well, that's all I have for you today. I will make this video available in My Open Math so you can watch it, because no one logged on, which was fine. I knew you probably wouldn't, because this is this is an out of school day for you all. But I don't want us to get behind, so please try to watch this. I'm going to try to send an email giving you some direction, because we had to miss today. But watch this video and fill out the information sheet and try the logistic growth homework set. And if you have questions, remember, you can always talk to me through email or phone, and I'll be back down your all's way in a couple weeks. All right. Have a good day.